So this is the title of my talk. So theory of frustrated superconductors and attempts by scientists who do not get that easily frustrated and continue to search for superconductivity at ambient temperature. This is going to be what I'm going to talk about today. Now we know very famous spin systems wherein this notion of frustration came, beautiful spin glasses. Then quantum fluctuations frustrate spins in triangular lattice, FCC pyrocolor lattice, and give it a spin liquid system. Then in the morning we had beautiful talks about Kitaev spin systems where you have spin liquid. So there are many interesting examples of classical and quantum frustrated spin system. And when you come to ferroelectricity, there are fascinating, not much attention has been paid. Many hydrogen bonded ferroelectrics, sorry for spilling here, they are all very frustrated. Even ice, when you go to very low temperature, when there is a tendency for ferroelectric order, but it never satisfies that. Dielectric constant shoots up, but there are lots of inherent frustrations. In fact, one of the early models due to Lee Bice model brings it out very clearly. Then even perovskites like strontium titanate, cubic perovskite, and barium titanate, they are very similar in terms of structure, and barium is heavier than strontium. And then this is a paraelectric, it never becomes a ferroelectric, whereas barium titanate is a good ferroelectric. So this is due to quantum fluctuation, so it never allows even a ferroelectricity to be formed, so it remains quantum paraelectric. So these are all well known. So what do I mean by frustrated superconductors? So if you take superconductor, electron-electron in Coulomb repulsion and electron lattice interactions frustrate superconducting order. For example, in cuprates, you very often see in the underdoped regime in terms of various experimental measurements, valence bond order, stripe order, spin order, charge order, and the structural instabilities. And this is what I said, that if you take a single layer viscose superconductor, TC is 5 Kelvin. Create a bilayer with almost the same normal property, the TC goes up to 160 Kelvin. And there have been non-reproducible claims of TC of even 200 Kelvin in the earlier times. It doesn't mean that it doesn't exist. The cuprate seems to have its own mind. We'll see what it is. And there are some people who claim that cuprates are failed room temperature superconductors, because if we take some of the theories seriously, the intrinsic TC can be as large as 300 Kelvin for the parameters that is available. But you never see anything above 150 or 60. Then very interestingly, you will find even a Fermi liquid phase, very well known to us in copper, aluminum, and so on, is a strange competitor to three-dimensional systems such as monovalent metals. This is what I will elaborate today. So this is the famous, now you can see the frustration in this cuprate branch, started at 23 Kelvin and then later it went down 5 Kelvin. Such a swing, as I said, in the normal state properties, they all look alike, almost alike. So something else is governing superconductivity or disturbing superconductivity. So this is a new diagram. Now this is what it is with the cuprate branch. Then there is this hydrogen under pressure. There is a claim from Ranga Dias, that TC is at room temperature. So it's a very fantastic situation for superconductivity. So from theory point of view, room temperature superconductivity, while some are stable, like under pressure, most of them are ephemeral, elusive, or unstable. There have been several examples. In fact, I will elaborate on some of them. The recently remarkable progress has taken place in hydrogen-rich materials under very high pressure, stable superconductivity. Not far from here, Indian Institute of Science, Bangalore, Thapa Pandey, Arindam Ghosh, and collaborators have seen unstable superconductivity even at room temperature in an unexpected place, namely silver-gold nanostructures. When you take a IBCO at room temperature, which is not superconducting, shine light of particular frequeny, femtosecond laser pulses, then it exhibits transient superconductivity lasting for 10 picoseconds. So this is, to that extent it is stable. Now from theory point of view, given the solid state and quantum constraints and electron pairing and delocalization, room temperature superconductivity is possible within certain quantum models and phases via, for example, RBB theory. And there are also theories, particularly due to Ashcroft, that hydrogen-rich system like solid hydrogen or hydrogen-rich materials, because the phonon frequency becomes very high, could become a room temperature superconductor. And there have been other suggestions like s-electron mediated pairing and so on. So to a theorist, it is possible, but for an experimentalist, it's a big problem. So when you get frustrated, what do? You meditate. That's what they say. It helps to cool down. So I meditated in the hot Sahara Desert when I visited Tunisia. My former student, Fethi, invited me. I spoke about room temperature superconductivity. And before that, this is a picture. We went to Sahara, which is not very far. So there is a paper which is available in the archive. You can look at it. How there are various routes offered by RBB kind of mechanism. And there is a lot of scope for higher temperature superconductivity. And Kopelevich, who is at Sao Paulo, he has written a very nice article, Unstable and Elusive Superconductors, collected historically claimed superconductors, and there has been many other claims later. And many people shy away from these experiments because they are not reproducible. We want reproducible and very beautiful things. But I will tell you that nature is not that kind. So it doesn't mean that we should ignore it. In fact, the story starts in 1946 with Richard Hogg. He wrote a paper. Look at the title of the paper. It's well before BCS theory. Bose-Einstein condensation of trapped electron pairs. So he thought that if electrons form a pair for some reason, it will become like a boson and it can undergo Bose condensation. He envisaged that possibility because what he did was he took liquid ammonia and sodium or lithium or these alkali metals very easily solve in it. And once it gets solved, the electron gets liberated, then you cool it down, it becomes a crystal or a solid, an amorphous solid, where what happens to the free electrons, that's what we will see. And Hogg claimed that he saw persistent current lasting for a few minutes at temperature as high as 200 Kelvin. He also saw it once in 30 samples, not always reproducible. Others tried it. They also did not succeed. And there are, stalwarts like P.P. Edwards and C.N.R. who have been continuing to work on it. The Rao's Institute is not very far, Jawaharlal Center, which he established. So now, what is actually going on? This system is this. Okay, this is what Hogg writes in his paper. The probable explanation for the above phenomena is to be found in the pair of trapped electron pairs, because there are experimental indications. Look at spectroscopically about trapped electrons. They form a singlet. And you can see the singlet excitation gap. So they form a singlet pair. Now this trapped electron pair, because of their zero angular momentum, such as pairs must obey Bose-Einstein statistics. This was Hogg's theory before BCS theory. So if you do a experiment, what you find is, or theoretical, detailed, sophisticated calculation, what you find is that trapped electrons form a spin singlet pair. And then if you do even more detailed calculation, what you find is they create their own way and form tubes in which these Cooper pairs delocalize. So from theory point of view, electrons are paired, they form very tight singlets. There is also possibility for delocalization. So nothing prevents it from becoming a superconductor. But however, there is a frustration, the medium doesn't cooperate. So lots of problems are there. So this is still an active field in some corner. And very soon, Antoniovich, this is a Nature paper, 2 articles appeared. What he did was he took amorphous carbon and did some experiments, and he reported it. He found Fraunhofer pattern in mimicking, like junctions like this. So this is what he wrote down. So he said this is superconductivity, but even he himself could not reproduce it. Others could not reproduce it. So somehow the superconductivity is frustrated. There are claims of cuprous chloride and cadmium sulfide, and recently graphite by Pablo Eskenazi and friends. So I will not go into the detail. So what is clear is that they see these things, but simply we have no nanoscopic control. That is the message. Because they are not reporting any wrong experiments. because there are obvious things like shorting and various electronic issues. They have taken care of that. But except that, we have no nanoscopic control, so things are not simply reproducible. To add to that came this beautiful result from Thapa and Pandey at Indian Institute of Science. Pandey is a solid state chemist. He's an expert in creating nanocrystals. Like a goldsmith, he can put in gold, silver nanoparticles, and he can do wonderful things. So for some reason, he did that and found that he created a situation in which there is a gold matrix, and then there are nanoparticles of silver of this dimension, about 5 nanometer. And then if you do various spectroscopy, you find almost silver with some contamination. I will show some other pictures later. What they found was, they found unusual signals for Meissner effect, which is not stable, and nearly zero temperature resistivity, noises, and so on. So they have several papers, I will come to it. So, for example, in one of their papers, the susceptibility dives down, and it's like a Meissner complete flux expulsion, but there's a lot of noise. And then the TC, the resistance doesn't become zero, but it's less than, much orders of magnitude less than that of silver or copper. And then resistivity fluctuates like this erratically. And then in a stable situation, if you follow a magnetic field, the TC does go to zero. So there is a, the magnetic TC does reduce. So there is a dependence of HC2 with, the TC with respect to magnetic field in the way that you expect. But then, of course, there are lots of criticism about noises were identical in shape memory, and we'll not go into the details because these friends have been doing this experiment for the last 4 years. They have improved the statistics. Once in 20 times they see it, and I do the experiment in this lab, I go to the next lab, I don't see it. So we do not know why. But the fact is, whenever they see it, it is there, because I have seen it in my eyes. So there, and this is one interesting example. Things cannot fluctuate more widely than this. This is an experiment from the result. And then, in a consoling way, if you look at some of these results, and then I will look at the detailed resistivity, depending on the current, there is always a maximum which is characteristic of granular superconductors in well-known established system. So there is something going on. It's very fair to say that we have no control. So we may be able to go to the moon, or we may be able to control several things, but we are not able to have nanoscopic control. Okay, look at one of these, volume susceptibility. It looks like this. So assuming validity of experimental results, it's clear that we are entering the realm of far from equilibrium phenomena, leaving the comfort zone of equilibrium thermodynamic phases. So what we seem to have is statistical superconductivity. So it's opening a new branch. Now, let me give an example of ice, where similar things happen, and then can come to superconductor. You know that ice is a frustrated system, because if you look at water molecules, there are hydrogen bonds, and hydrogen bonds can be with respect to this molecule or that molecule. So there's a lot of quantum dynamics. So consequently, ice has at least 15 equilibrium phases, including amorphous ice phase. And there are also called water wires. And in the biological system, it has a much richer variety of equilibrium structures. So if you look at the phase diagram of ice, I took from the encyclopedia, you have the standard liquid and vapor, liquid and vapor, and then you have standard ice, 1H ice, 1C, 11 ice, so at least 12 phases. And then in addition, if you quench it, you have glassy water or glassy amorphous ice. Now, if you look at in terms of free energy and landscape, as a function of parameters like pressure and configuration coordinate, it's very clear water that we use is the equilibrium thing. But if you look at the free energy landscape, there are many, many minima, metastable states, which can be stabilized by applying pressure and various manipulations, and temperatures and various manipulations. So the question is, can this be stabilized under some equilibrium? So can I take water at room temperature, then do some magic to it and make an ice out of it? And apparently it is possible. So when a system is disturbed or taken out of equilibrium, in fact, there is a very nice book about water and snow crystal by Ken Liebrecht from Caltech. It's a freely downloadable book. It's a very delightful book it starts about, what is that? Snow crystals, snowflakes, very origin of patterns of snowflakes, and talks about physics of ice. Okay, so this is what we already saw. So Arindam and Ghosh and Tapan Pandey company have seen this. So let us try to understand what is gold, silver or gold. It's well known that both silver and gold never become superconducting. People have gone to the lowest temperature possible. That was always a puzzle. And people like Morel and Anderson rationalized it by saying that long-range Coulomb interaction comes into play, and because of retardation effect and so on, the effective electron-phonon coupling gets renormalized down by what is called Coulomb pseudopotential. And they gave a theory which says TC will be very small or vanishingly small. But I was never happy with that theory. I remember I have discussion with Anderson, because to me, if you take silver, it's a half-filled band of s-electrons. It's well approximated, because if you look at the Fermi surface, there is only one Fermi surface at the Fermi level. There is only one band. So that if you go down, there are other bands. So it's a good approximation to describe this s-electron system in terms of tight binding model with some hopping parameters and bandwidth. But when you do that, what is remarkable is you start with the Hubbard model, for example. There is a substantial U, but then because you are living in 3 dimension, very simple renormalization group analysis shows that Coulomb interaction becomes irrelevant, and you have a beautiful and robust Fermi liquid consistent with the experiments. So Landau wins. So Fermi liquid theory is stable at low temperature. Basically because in the sense of renormalization group, U gets renormalized to 0. But however, so all monovalent metals, look, they are all half-filled band system, essentially one band system, but in 3-dimensional bulk, the U gets renormalized down to very low value, and then you have this physics. So the question is, behind this below this conformity, are there some interesting superconductivity going on? Why did I ask that question? Because we'll come to it. There is a very early work by Al Overhauser from Purdue, who used to be at Purdue. In fact, I visited Purdue once and I had a delightful discussion with Overhauser. He told me that don't waste your time working on RVB theory. Look at metals. I didn't take it very seriously at that time, because according to him, he has a book actually. Simple metal like sodium or potassium is not simple metal at all. There is a lot of spin density wave and charge density wave correlations. And because of some frustration, they have died, and you will end up because he has at least 20 experimental anomalies, which he says cannot be explained without invoking fluctuating spin density wave and charge density wave correlations. So while at low energy scales, it's a beautiful Fermi liquid, quiescent Fermi C. But if you go below, there are strong undercurrents, supercurrents. That is what Overhauser said. And then there was a very famous experimental thing called Mayer-Elnaby resonance. What you do is you look at optical conductivity. You find a very strange anomaly which cannot be explained by Jellium model or any known model. So then came Marvin Cohen. So Marvin said that he did some many-body calculation. He said that yes, at the level of Fermi liquid, quasi-particles very weakly interact. So there is no pairing, even electron-mediated pairing is not there. But however, if you go to high energy scale, at short time scale, the quasi-particles have very strong interaction and attractive interaction. So he said, I could make everything agree with experiments if I assume that there is pairing, there is a pairing as a function of momentum, I cross the Fermi surface at k. So I have positive amplitude for pairing, negative amplitude for pairing. So I have 0 amplitude at Fermi surface. So this will make it look like Fermi liquid for all practical purposes. But however, if you do spectroscopy, you'll see signatures of this pairing, which he associated with Meir el-Nabi reference. Nobody else read about it. I knew about it. I had talked about it with Marvin many years ago. If you take a standard superconductor, the pairing takes place only close to the Fermi surface. So, according to Marvin Cohen was a student who is at Berkeley now. Marvin Cohen who was at Chicago and later at Exxon. So, there is a lot of pairing activity, but well below the Fermi surface. Okay. So, I have 10 minutes, 5 minutes for this. Okay. Now, I realized, okay. So, this is the story. So, the most important point is you have a half-filled band. Now, let me take a chain of gold atoms or a chain of silver atoms and then do a very simple-minded theory. So, which is what I did. So, if you take an ideal chain, of course, it may be unstable for various reasons. In fact, it's very interesting that there is an experiment in which you have take gold, pure gold is malleable. So, you drop pure gold, it becomes thinner and thinner, and then you have a gold chain, nearly monoatomic chain of some nanometer dimension. And people have studied various aspects of that. So, gold has a tendency to form chains, but at short length. So, if you do a very simple-minded theory, the hopping parameter is this as inferred from band structure, and the U various. What I find is gold chain will be a Hubbard model with a gap of 1 electron volt Mott Hubbard gap, and the exchange is 1.5 electron volt. And there is experimental confirmation for this because gold molecules have been produced. So, 2 gold atoms, because there is an unpaired 2 electrons on that, they form a hydrogen-like molecule, and it's stable. And the single triplet gap is close to the data to about 1.5 electron. Similarly, people have studied experimentally and theoretically gold and silver clusters. They have a strong tendency to form singlets, and the singlets resonate and so on. So, if you take silver or gold, and if you form a chain, it's a Mott insulator. It's very different from what you see in 3-dimensional bulk silver or metallic gold. It's lustrous, it's conducting, it's a Fermi liquid at low energy scales. So, this shows that if you can disturb 3-dimensional silver or gold, there is a possibility of some metastable states of superconductivity. I will come to it. So now what I did was a very simple thing. I studied a 3-dimensional system of weakly coupled chains of silver and gold by hand. Then you find superconductivity at room temperature is not a problem at all. But unfortunately, nobody gives us such. Nobody is able to make silver chain, or nobody is able to create such a thing. Okay, this is in 1 dimension. So emboldened by this, I went to 2 dimension, because 2 dimension is also a situation where strong correlation effects become very important. Whereas in 3 dimension, it requires too strong a correlation to have Mott insulators and so on. So if you look at a triangular lattice of Hubbard model, what you find is there is a critical U above which you have Mott insulator, you have doped Mott superconductivity. And then if you look at the value of U for silver and gold, it's way before Mott localization. So you have essentially a Fermi liquid in 3 dimensional, like similarly in 2 dimension. But however, if we study the problem in 2 dimension with extended Hubbard model, which has unscreened Coulomb interaction, what you find is the critical thing go down. And then what is remarkable is you have a first order Mott transition from separating Mott transition to a metallic state. Now, if you analyze this carefully, this is what I call self-doped Mott insulator, where you have created spontaneously a small density of electrons and holes, holons and doublons, and they run in the background of this Mott insulating matrix. So you can now do some theory and find that even in this region, which used to be a Fermi liquid metal, now it can become superconducting with a comfortable TC. So the message is silver and gold are beautiful Fermi liquid, which is true at low energy scale. But as you can see, even in renormalization group analysis, you start with some initial parameters in a Hubbard model. You have many fixed points, Mott insulating fixed points and so on, but they are never reached. And finally, you reach very quickly Fermi liquid fixed point. So this existence of various fixed points like Mott insulator, spin density wave, charge density wave, fixed points are like metastable states in the system. So I will come to it. So this, sorry, I'm sorry about it. So all this analysis essentially points out that even three-dimensional metal like copper or silver or gold have beautiful Fermi sea at low energy physics, but when you go to high energies, if only you can stabilize them through many body localizations or various things, it is possible to reach them. And my claim is, yeah, since I am just a few more minutes, what I did was, Pandey, Tapan Pandey and Arindam Ghosh and company have unintentionally created subsystems which are chains and planes which have created superconductivity. So just to give you one example. So, these are all FCC systems. So they are stacked like this, triangular lattice are ABC, ABC. I'm trying to find faults with this. So finding faults, for example, if you have a stacking like this, is called a fault. Apparently Aristotle said between two correlated faults lies virtue. Okay. Now I'm going to say between two faults lies ITC superconductivity. For example, if you take, it's a metastable state, two triangular lattice layers sitting on top of each other, and then with a B lattice and CC, then by calculation you can show this essentially gets gapped because it's a half-filled band system, and because there is a direct communication between the two electrons, there is a Haldane gap-like phenomena here and here. So you have a protected B layer. So now when you look at since because of time I'm rushing and I'm sorry, correct, sorry. So if you look at simulations that are available about gold nanoparticles, you find lots of faults. So Thapa and Pandey have created this situation because now in fact there are electron microscope which I have analyzed, like if you look at it, there I can find many stocking faults. So to me, they are sources of local pairing because of the two-dimensional, one-dimensional physics. So what you have is basically a Fermi sea, a calm Fermi sea, which is disturbed by these local stacking faults and the two-dimensional and lower dimensional system where there can be enhanced superconductivity. So the frustrated superconductor can come up here by holding hands through proximity effect, and you can explain what has been observed. So this is what I wanted to say. I'll be very happy to answer any questions. Sorry, I have taken too much time at the beginning because of my fault. So.
Okay, thank you very much for this talk. It's really interesting to think about novel ways to superconductivity. Are there questions? Okay.
There is a question.
There are questions.
So as you said that in the normal state, most of these materials, they have very similar kind of behavior. So I mean,
cuprates, particularly.
Cuprates.
Yeah,
I'm
right.
talking about cuprates only. Yeah. So I mean, what particularly might differentiate what happens as you go from
exactly.
this state to the superconducting state?
For example, if you take one layer bisco, they are, as you know, there are local octahedra which form a square lattice. In single layer, this octahedra have a very strong tendency to tilt. So a tilting can localize a bond. So the charges which are running around freely get localized into singlet bonds, and you have stripe order tendency. Now if you have a bilayer, this octahedral tilt is immediately removed because it's not a octahedra, because it's a semi-pyramid. So immediately the TC jump from 5 to 90 Kelvin. I have estimated how this octahedral tilt, if you stiffen it, TC can go up. Just to give you another example, there was a beautiful work by Nato and collaborators. They took lanthanum copper oxide with optimal TC of, the TC was 20 Kelvin. Then they took the same crystal and put it on a substrate which had an epitaxial strain, which amounts to applying a hard lateral pressure. And the TC went up to 40 Kelvin. Just an epitaxial strain. So that means the single this LCO system, you had this octahedral rotation and stripe tendency, it goes up. So similarly, if you put 3-layer and 4-layer, the stripe tendency in the middle layers are even much less. So that's why, for example, in the famous mercury superconductor with 3 and 4 layers, the carrier density is optimal at the middle and lower on the top and bottom, and it suffers less frustration, and the TC has gone up to 160 Kelvin. And there was another experiment, somebody did it, they poured water in IPCO, and the TC went up. Please don't laugh. It was an experimental fact, and somebody put alcohol also, TC went up. The physics is, it's also, in fact, similar thing happened in sodium cobalt oxide system with layered material with water, because the intercalated water offers high dielectric constant, and they reduce this charge order tendency. So they help suppressing one of the competitors.
Okay, thank you. More questions from the audience?
Thank you. Oh.
If I understand you correctly, you mentioned that gold becomes a Mott insulator if you stretch it enough. I mean,
Exactly. With the so if you can form a monoatomic chain of gold, do a simple theory, it's a Mott insulator with 1 electron Mott-Hubbard gap. Yes, that's a theoretical fact, but nobody has been able to create long chains of isolated, whereas people have been able to create free-hanging copper sheets. In fact, it's a very nice method. There's something called de-alloying. You start with copper gold alloy and remove gold. Then you find voids which contains two-dimensional sheets of free-hanging copper. Now, you may ask, why don't I put it on a substrate? Yes. What happens is, electronically, it gets contaminated. For example, even if when you put it on insulator like silicon dioxide, some of these dangling bonds strongly bond with the s-electron, and the physics becomes very different. So unless you take care to insulate it, so this is what I have been telling my experimental friends, but nobody has listened to me. Please create a free-hanging silver or gold. There is some gold mine there, superconductivity. By the way, I told my wife that I will give her a silver chain, nanoatomic chain. She asked me, will it glitter? I said, no, it's a Mott insulator. She said, no, I don't want it.